So here's our example of a matched pairs experiment. You have subjects, they're trying to raise their ACT test scores. They take the test, we have their initial scores, and then they take a prep class, and at the end of the class, they take the test again. We measure the difference of scores. The differences will be our set of data that we analyze. So here's the stuff that's reported, before and after. And then here's the differences that we're talking about when we do matched pairs. And then we say the company advertises an average of a 2-point increase based on their test. So we'll set the null hypothesis to be mu equals 2. And we're wondering, is it just not quite that good? Because they might be overstating their case. So we'll take for the alternative, the mean is less than 2 on average. Because we think maybe they're overstating their claim. We'll go ahead and compute the t. The null hypothesis is 2, it goes here, x bar there, s there. There's 9 values, 9 differences, square root of 9. Square root of n goes there. We compute x bar for the differences. Sometimes I'll write it like this, x bar for the differences, s for the differences. Just so we know we've already done some work in advance. We put those numbers in, we get -1. That just happened by accident. Came out to be -1. And then, really, -1, does that even make sense? Oh, I see. So x bar is about 1 2/3. You subtract 2 off, you get -1/3. And down here is 1/3, so -1/3 divided by 1/3 is -1. It works. We find t star in row 8 of the table. Since the sample size is 8, the degrees of freedom is 1 minus 8, which is, 9. So the degrees of freedom is 1 minus 9, which is 8. If that row didn't exist, we would use the next smaller degrees of freedom. So if if 8 wasn't in the tables, we'd use 7. Sometimes you'll get like 42 degrees of freedom. There's no 42 in the table, so you just go to the next smaller numbers, might be 40, that would show to you do your calculations. So go across that row of the table, I'm looking for -1. Of course, I don't see any negative numbers, so I'm looking for 1. I'm looking for t star values that are on each side of 1. So here is 899 in one slot for t star, and here's 1.108. Those two values bracket the -1. And they allow us to then compute the tail probability approximately, because here's the tail probabilities for those kinds of numbers. So for 899 and above, or -899 and below, the area is 0.2. And for 1.108 or -1.108, that far up or that far down, it's 0.15. We have a one-sided test, so it's one tail. It's less than, so we go less than. So we want the area left of -1. So I'm going to compare the areas left of -899 and left of -108. And those areas are 0.2 and 0.15. So the p-value is somewhere in here between those two numbers. So it's bigger than 0.15 and less than 0.2. And bigger than 0.15 is bigger than 0.05. So the claim stands. HO is not rejected. The evidence doesn't show that the long-term mean is necessarily less than 2. Our sample mean is less than 2, but that could just be due to random variation. Where did it go? Here it is. 1.67. Even though the long-term mean is 2, it's conceivable that a sample mean with 9 values could easily be less than 2 or greater than 2. And so what this says is it'd be pretty easy to get this kind of number for x bar if the long-term mean was actually 2. So we don't have any reason to reject the hypothesis that the long-term difference, because of the prep class, is about 2 points. Alrighty, so we just did a matched pairs, and we did one where the null hypothesis mean wasn't 0 because there was a claim of an increase. We're trying to refute that claim, thinking they're overstating their case. We're unable to do that because random variation, if mean was 2, could easily be responsible for the data. Alright, almost done. Keep going, keep going. I'll be back in a minute.